Hello, and thank you everybody for coming. My name is Jeff Lyon. I lead the AWS DDoS response team, who is responsible for protecting AWS, Amazon.com, subsidiaries against the availability impact of distributed denial of service attacks. I'm joined by my colleague, Andrew Kiggins, a security solutions architect, and also two of our customers. I have David Grandpa with typefrag.com, and also Adrian Newby with Crownpeak. I know that protecting the availability of your applications is of critical importance to every one of you. I also know that for many, the recent trend in IoT-sourced distributed denial of service attacks is of significant concern. Today, I want to give you the confidence that you can mitigate these attacks and protect your applications in the cloud. And despite the recent increase in size and frequency, we continue to see these attacks across 5 major vectors, and we're going to go into those momentarily. And we're going to talk about those in terms of 4 major use cases. Adrian and I are going to talk about web use cases, and Andrew and David are going to talk about EC2 use cases. So let's briefly go over the different attacks, and that'll allow us to have a deeper discussion about the methods that we're going to use to mitigate them. So traditionally, we've talked about DDoS attacks in terms of layer 3, layer 4, or layer 7 attacks. But I find these things to be somewhat esoteric. Instead, I want to talk about them simply as attacks that cause large volumes of traffic, large volumes of connections, or large volumes of requests. And the first attack that we're going to talk about is a UDP reflection attack. This is the most common attack that we see on AWS. And it's also my favorite. And I'll tell you why I like it. Because in order to generate this attack, an attacker has to spoof your IP, send it out to tons of servers across the internet, and cause those servers to reply with a flood of traffic. This gives us a really clear signature on which to mitigate the attack, and we know that the traffic that we're receiving is not spoofed. And here's just an example of that traffic. And we see that it's on the UDP protocol, that it has a clear signature, in this case, port 1900, which is SSDP, and a large packet size. So when we see this traffic, we know that we have a few attributes on which we can mitigate using something like an ACL or a shaper, for example. And we also have UDP floods. These are pretty similar, but they're a little bit more ambiguous, and they come from the ephemeral port range, because somebody is just spoofing packets and sending them at your application. And we see that here with the different ports. That attack is also fairly easy to mitigate if you don't require UDP traffic. But then that brings us to TCP SYN Floods, which is probably the next most common that we see. These attacks are a little bit more difficult in that they're a flood of traffic, and they're also a flood of system connections. So the attacker is not only trying to generate a large volume of traffic, but they're trying to exhaust the state table of your server or your firewall, for example. And here's what that looks like in a netstat. So we see that it's TCP, and we see that there are half-open connections. So we have a clear signature. It's just a little bit more difficult to do something about. But I'm going to get to that shortly. And then we have web application layer attacks. These are a bit more challenging even than the TCP SYN flood. And the reason is that these attacks look just like your legitimate traffic. So one method that you can use to mitigate it is if you do have a signature, something in the header or the source IP address, then you can block on that. But if you don't, you want to use your WAF to do something like rate-based blacklisting, where you define some parameters of what malicious traffic looks like and then automatically block. And then we have DNS Query Floods. DNS Query Floods are very similar to web application layer attacks in that they are many legitimate requests. In this case, legitimate DNS requests. So there's different ways that we can deal with this. If it's just a regular DNS request and it's coming from a source that we know is malicious, we can just block it. But sometimes that's not always the case. Sometimes the request comes from a known good DNS server. So what do we do about that? We look for something called a cache-busting attribute, because what the attacker is trying to do is to get through that recursive DNS and compel your authoritative DNS to respond to the request. So when we see this randomness, we know that probably wasn't a real DNS request, and we're going to go ahead and block it. So let's look more specifically about how we do this on AWS. So conventionally, if you wanted to mitigate an attack on your own data center, you could do a couple of things. You could deploy your own DDoS mitigation systems, or you could use a commercial DDoS mitigation service. These services allow you to route your traffic through their cloud externally, scrub the bad traffic, and then let the good traffic through to your service. The challenge with this is that it can add additional latency, and it can add additional points of failure if that service were to fail, or even if any intermediate network were to fail while it was handling your traffic. On AWS, we wanted to build DDoS mitigation that was built into the AWS global infrastructure. We wanted fast mitigation without external routing, so we wanted to minimize that latency impact. And we wanted to protect your availability and also your throughput. So let's look specifically about how we do this on AWS. We found that relying on commercial systems was a little difficult because we run into scaling challenges. When you grow at the rate of AWS, it's pretty difficult just to pick up the phone, call a vendor, and say, I need some huge number of DDoS mitigation systems. We found that this kind of thing just wasn't practical for us. So instead, we built a system internally that we call Blackwatch. Blackwatch mitigates very large volume DDoS attacks, and it has three basic methods. It allows only that traffic that's intended for the service, and for those SYN floods, it uses a combination of SYN proxy and SYN cookies to verify that the connection to the service was a real connection that we intended and wasn't from some spoof source. And then we use something called suspicion-based traffic shaping. So for example, like when you have a DNS query flood, we want a way of scoring that traffic across multiple dimensions to know whether we think it's legitimate, or we think it came from a real user, or we think it may have been part of a DDoS attack. So we look at things like abnormal sources, abnormal geos, abnormal port and protocols, or other characteristics, like the cache busting, for example, that we just found to be odd or unusual. And most of all, we leverage the scale of AWS to minimize false positives. So if we're able to, we always just want to let all the traffic through, and we're only going to apply a mitigation where it counts the most, where we need it to protect the availability of the service. So here's an example. I took this screenshot of a real attack, and you can see that we identified the DDoS because it fell into one of those low priority bands. And then towards the bottom of the screen, you see all these other colors of traffic. And what that's telling us is that the traffic is either most likely the real traffic you intended towards your service, or maybe there's some DDoS in there. But we found that by deprioritizing only the most suspicious traffic, we can achieve a very effective mitigation and ensure that we're not causing false positives to the service. So let's look at the common use cases. Let's look at how do you build architectures that allow you to take advantage of these mitigation systems. So a common use case on AWS uses EC2 instances, VPC, and perhaps an application load balancer. So you're able to take in significant volumes of traffic towards your service and distribute those across EC2 instances. And if it was some source port or protocol that you didn't expect, then you can go ahead and block that using your host. Or if it was a protocol or source you didn't expect, you could block that in your VPC using security groups or NACLs. But say there's a DDoS attack. If it's not blocked by your VPC security group or your NACL, then the application load balancer is going to start scaling out to absorb that volume of traffic. And when it gets to be a very significant volume of traffic, we're going to use our Blackwatch system to mitigate it and protect the availability of that load balancer. And when you host in AWS, you're not just getting the AWS region. You're not just getting some set of availability zones. Rather, you're getting many diverse internet paths that give you a lot of throughput and a lot of redundancy to many different internet exchanges. So you can take advantage of not only the capacity that's available locally, but the capacity that's available elsewhere out on the internet. But we like to suggest that you take this a step further and use what we call a highly resilient web application. So instead of allowing attacks to come to you and target your origin, you can use services like CloudFront, Route 53 to push out the distribution of your application toward the edge. That means getting that application close to your end user, optimizing for availability and performance. And it also allows you to use the AWS WAF service. So if you have a set of web requests or some key that you want to block on, you can do that using the WAF, using something like a string match condition. And we also have something that you can deploy called AWS WAF Security Automation. And that allows you to define all types of pre-configured rules to include HTTP flood protection right there in the AWS WAF. And so instead of asking your customers to come to you, we recommend that you go to them, distribute close to the source of the traffic, and mitigate the DDoS attacks close to where they originate. And so here on the screen, I just gave some examples of different AWS regions or different geographic regions where we have AWS edge locations. So we have over 60 of these today. So if an attack is originating, for example, close to Dublin, we're going to mitigate that using the Blackwatch capacity in Dublin, and likewise for every single edge location that we have. And that's going to allow you to cut down the latency of distributing content to your users. It's going to allow you to optimize for throughput, and it's going to keep that DDoS traffic far away from your origin. And so at every one of these locations, we have those Blackwatch systems on site. So we're not having to distribute those or distribute the traffic to other mitigation systems in other geographic locations. And you can see from this map that we have many of them. In many cases, we have many Blackwatch systems in a single edge location or in a single transit center serving an AWS region. So at this time, I'd like to take the opportunity to introduce Adrian Newby with Crownpeak, who's going to talk about how he helped one of his customers mitigate DDoS attacks in the cloud.
Thanks, Jeff.
Thanks, Adrian.
Hi, everybody. Those of you at the back, can you put your hands up if you can hear me? Excellent. So, DDoS, exciting and cool, where everybody wants to be part of it. Who knew? I've been in information technology probably close to 30 years, and this is the first time I've ever been with the cool kids. For those of you who don't know the name Crownpeak, we provide web content management services to our customers. All of our services run under Amazon Web Services. And our customers use our service to build, deliver, and then maintain websites all around the world for all different types of businesses. We have small customers, we have large customers. Particularly, we have a lot of large customers in regulated industries. And one of the customers that we've worked with for a long time is the Bank of New York Mellon. For those of you who maybe aren't aware, I learned a term a couple of years ago, SIFI, Systemically Important Financial Institution. A financial institution that is so significant to the performance of markets around the world that there would be a significant disruption if anything bad happened to it. So we tend to pay attention when the Bank of New York calls. And they are the largest holder of assets under custody or administration. They operate in hundreds of markets worldwide, and many of the bank's websites are hosted and managed on Crownpeak. Well, what's really cool about the Bank of New York is that they really take their role in the world financial market very seriously. And they are up, down, and sideways throughout all of the divisions of the organization, really, really committed to leading the world and being best in class when it comes to cyber defense and threat protection. And so the case study that I'm going to talk to you about today, I'm going to walk you through some of the work that we did this year, actually, enhancing the threat protection that was already in place and demonstrating and proving the kind of attacks that infrastructure could sustain. And so Jeff, a moment ago, outlined a basic architecture. And if any of you were here at reInvent a couple of years ago, we were here talking a little bit about some DDoS work that we'd done a couple of years ago. And this was the kind of architecture that we were working with at the time, using CloudFront in front of the web or the application server environment to provide a degree of protection, and then building effective auto-scaling behind the CloudFront distribution. And that worked really, really well. But when we started working with the Bank of New York, and in the couple of years since we first started really getting serious about DDoS, we've been working pretty closely with AWS, and we're really excited about the new facilities and capabilities that have come in with the introduction of services such as Lambda, such as WAF, the Web Application Firewall. And we wanted to see what those services in particular could do to improve the response to a cyber threat or a cyber attack. So we also deployed a more advanced, or what we call a hardened architecture, which really attempts to exploit what those services can do. And in this diagram here, you can see that the Web Application Firewall is the key component that we introduced. And what's actually happening in this picture is, as all of the traffic from the DDoS attack is coming in to the Web Application Firewall, and as traffic gets passed through the firewall into the CloudFront distribution, we're intercepting the CloudFront logs in real time, sending them to S3 storage, and as they arrive in S3, they trigger Lambda functions, and within a Lambda function, we can apply all sorts of analysis, pattern recognition, aggregate statistics, responses, and not only accept or deny each request as it comes in, but actually modify the behavior of the WAF in real time. And I'll show you a little bit how that works in a moment. So the actual testing that we structured took place over a couple of days. By the way, a tip for all of you that might want to try this at home: if you even think about doing this on AWS, make sure you pick up the phone and give AWS a call first. Otherwise, you'll find your account privileges evaporate very, very quickly, because AWS is paying attention to DDoS-like behavior these days. So the basic structure of the testing that we performed with the Bank of New York was, first of all, to get a baseline, to kind of get a sense for what kind of traffic we would have to put into the front end before the mitigation strategies that we had in place would begin to activate. So that was our baseline, using simple HTTP GET requests. We also performed a Hulk test. For those of you who aren't familiar with the term Hulk, HTTP Unbearable Load King, which my team rehearsed me on for several weeks before I actually got up on stage to make sure I said it correctly. And we actually worked with another really cool company in this space that really specializes in this kind of cyber threat protection and testing by the name of Red Wolf. And they actually have taken some of the Hulk testing software that's freely available on the internet and juiced it up a bit to add additional attacks in, for example, obfuscating the source client, doing forging HTTP referral headers, and so on and so forth. And then, just because we had some time on our hands, we also really started hammering the web application firewall to see how hard you could push the service and whether it really did scale to the level that it needed to deal with the largest attacks that are taking place in the world today. I'm not going to go through all of this with you today, nor actually are we going to do an attack in real time. I did think about that for about 5 seconds, and then I also thought that possibly being videotaped while launching a deliberate denial of service attack on one of the world's most important financial institutions was not a career advancing strategy. So we won't be doing that, but we do have a movie. And in the movie, I'll show you a little bit about how an attack evolves and how it works in practice. But these are the kind of metrics that we were working with when we actually performed the test. Attacks from 200 different concurrent attack vectors, pushing requests up to, at the peak, over 1 million requests a second, returning up to 50 plus gigabits a second of data, sending almost 5 gigabits of data into the environment. So these, by any stretch of the imagination, are significant numbers. And this is the instrumentation that we typically work with when we're evaluating the quality of a cyber threat resilient solution. And this is really a mashup of several different pieces of instrumentation. At the bottom left of the screen, you can see your typical CloudWatch metrics. I think in this case, we've got across the top row, CPU utilization, network utilization. The right-hand one is ALB queue latency, which is an important thing we'll come to in a minute. And then at the bottom, instrumentation for the autoscale pool, which tells you how many instances are in service responding to the incoming traffic. On the right-hand side are some pieces of instrumentation from some of the Red Wolf testing software. We have just raw data volume at the top. In the middle, we have number of packets going into the environment, and at the bottom, we have the number of concurrent TCP connections. This is the technical part of the demo because I have to start this movie while I'm actually talking. So there's my little mouse cursor going across. Hopefully that's working fine. And then at the top, as the attack starts, we have the Crownpeak instrumentation where we're harvesting CloudFront logs and harvesting CloudWatch metrics in real time, sending them into the Crownpeak data management service, and then surfacing them on a Grafana dashboard. You can see that it'll flash up there that shows how, as the attack begins, the autoscale pool is default starting at 6 instances. And already you can see CPU stress in the back end of the environment as we start ramping up the Hulk attack is beginning to work the back end quite hard. You can see CloudFront requests in the top part of the dashboard coming up. We've already scaled the autoscale pool to 15 instances. So we've already almost tripled the amount of back-end server capacity very, very early on into this first level attack. This attack, by the way, is the baseline architecture, which doesn't include any of the web application firewall stuff, which is why most of the top dashboard isn't actually showing anything yet. You can see here, already in the ALB backlog queue, at this point in the test, we were already backing up requests in the Elastic Load Balancer because there weren't enough instances available to service the requests. We're getting up to a fairly significant portion of CloudFront requests, as you can see there. And there's a lot of activity in the back end, a lot of scaling activity. One of the things that we notice consistently is although the back end scales in response to increases in CPU network traffic, there's a latency. So we were seeing of the order of 60 seconds lag between an auto-scaling event and those instances coming into service. We can see here spikes in the delivery of network packets trigger additional instances that are put into service. At the end of the test here, we're getting to something of the order of 30 instances. Lots of requests hitting the CloudFront edge distribution. And at the peak of the test, I think in this first phase where we're just exploring the baseline architecture, we were hitting something of the order of 80,000 packets a second. So not bad. A couple of things that we observed during that baseline test. Although the application scaled mostly, we did see users experiencing problems, timeout requests occasionally, lags in the back-end scaling. So we figured that we could probably improve the end user experience by adding some web application firewall capability. The first thing that we did is we used some of that Lambda-based CloudFront log analysis to blacklist IP addresses that are originating disproportionately high levels of traffic. We also built a rule set within AWS WAF to detect SQL injection attacks, cross-site scripting attacks. And we also did some work to discard large URLs, large URIs, because random URL request forgery, forcing the back end to deliver 404 requests, is one of the easiest layer 7 attacks. So with the WAF in place, as the major attack begins now, you can immediately see in the top part, you can see how the web application firewall is beginning to intercept these attacks. We're only a brief period in, we're already intercepting something of the order of 9 million illegitimate requests a minute, many of which are those random URLs that are being generated. And also, we found very quickly that the rate limiting rules that we had built in to isolate individual IP addresses were a very, very big factor in eliminating illegal traffic. At this stage in test, as you can see, Lambda has already blocked around about 175 of the potential maximum 200 attack vectors that we had in test. So neutralizing almost all of the malicious traffic immediately. At this point in the test, we're about halfway through. CloudFront is now dealing with around about 10 million requests a minute. If you think about that, that's a ridiculous volume. But while all of those requests are being discarded, WAF is still smart enough to let the legitimate traffic through to the back-end web application server. And so legitimate users are still seeing perfectly good response times. No backlog in the ELB request queue, so no end users getting timeouts, no lack of response in the browser. Throughout this entire test, the website was delivering sub 1 second response time. Most importantly here, we never ever hit the auto-scale threshold once. So despite this dramatically larger test in the second phase with the WAF in, we never triggered the auto-scaling group. At this point, we're handling almost 100 times the amount of traffic that we were able to handle in the first phase of the test with no discernible degradation of service in the back end. So, and as the test concludes there, I think you can see some pretty impressive results and also some pretty powerful benefits that accrue just by applying the new web application firewall technologies. In particular, much reduced costs in the back end because you're not dealing with all that auto-scaling. I thought we might give you a little bit of a glimpse into how far you can actually really push these technologies. This is the scenario from all of the testing that we performed. We were blocking hundreds of IP addresses. On the top right-hand side there, you can see we were able to filter out almost 50 million illegal requests a minute and still let up to 20 million requests of legitimate traffic come through. In the bottom left, you can see 3 types of rules that were firing. The green rules are the IP addresses that were being blacklisted. The blue dots are SQL injection attacks, cross-site scripting attacks. And just a little bit of orange there in the bottom left, which is some SQL injection attacks that were also blocked. But I think the most powerful metric on this particular slide is the one in the bottom right, where we were able to handle traffic of the order of 100 million individual HTTP requests coming in every minute, which is profound. So I think in conclusion, I think the opinion that we would express and that we would offer to you is that thinking about deploying CloudFront and the web application firewall offer some really significant benefits. Not only are they really strong defenses against layer 7 attacks in the case of the WAF and layer 3, layer 4 attacks in the case of CloudFront, but they can also benefit you and your customers in other ways by reducing the amount of cost that it takes to scale the back end. If you are planning on experimenting with this kind of technology and this kind of approach, we have a couple of things that we learned from our time. Most of the easily available attack toolkits on the internet do a lot of their layer 7 attack, generate a lot of their layer 7 attack traffic by randomly generating super long URLs. So limiting those query strings and sterilizing the headers that you're processing and passing through to the back end can really eliminate lots of common attacks. Another thing to think about is really take advantage of what something like CloudFront will offer in terms of implementing redirection from HTTP to HTTPS. I'm sure most of your web services today have some kind of redirection in place. Doing it at the edge in the cloud shields the origin not only from all of the traffic that's involved in terminating the SSL traffic, but also shields the back end from all of that redirection activity, which can be a big deal in the middle of a DDoS attack. And lastly, for those of you who haven't yet embraced SNI, I would say embrace it, because one of the things that we found is that most of the many of the commonly available DDoS toolkits out there, even today, don't implement the TLS handshake properly that is required in order for an SNI-enabled website to function correctly. So just moving to SNI can essentially take you out of the attack trajectory of many common attacks. So hopefully that's been a little bit useful. I'd like to hand over now to Andrew, who's going to talk to you a little bit about EC2-based defense techniques.
Great. Thanks very much, Adrian. That's excellent. Wow, great turnout. I'd just like to add, this is a shameless plug for a presentation tomorrow. We're actually going to talk about how to secure your web traffic with CloudFront. We'll talk about Amazon Certificate Manager, we'll talk about Red 53, we'll talk about the registrar, and how you can use that to secure your workload. So shameless plug there for tomorrow. Attend that if you can, and this is something interesting. So I think what you've heard here is there's some great services in AWS to help protect yourselves and your customers and your applications from DDoS. And unfortunately, there's workloads in there that are a little bit different. Maybe they're not web-based. Maybe they've got a proprietary protocol. Maybe you can't take advantage of some of the AWS services that you've seen today. So I want to talk a little bit about that. If you've had a security conversation with any of our security SAs or with your account reps, you'll have heard them talk about the shared security model. And the shared security model really talks about the things that AWS will do to help you protect and the things that you have to do yourself. I'm going to dig into a little bit about the things that you can do with your architecture to help yourself. First thing I'd like to know is, and this is really pertinent, how many folk in the audience are gamers or have played first-person shooters? And I know you're out there, don't be shy. Come on, put them up. OK, now, how many of you have been seriously fragged by a 13-year-old and launched a stressor tool to take them down? And I know I'm not the only one. Come on. Yeah, so that's a DDoS attack. And unfortunately, it doesn't matter that he was 13. He's faster than you. My son teaches me that regularly. But it's a very important thing because the gaming companies really have it hard. And they're almost the poster child for problematic DDoS. But before we get into that, I want to talk a little bit about how networking works inside AWS. I'm going to talk about flow logs, security groups, and NACL. So if you've got a strong networking background, this is the time to take your nap, because this is meat and potatoes for you guys. So one of the things we have to look at is how traffic flows in and out of your application. AWS has abstracted a lot of the networking facilities that you've been used to in your on-prem environment or in your home. And what we get instead is VPC flow logs, security groups, and NACLs. And they're a great way for constraining and controlling your traffic. So the first thing is security groups. For anybody who's been in AWS for less than about 3 years, this is kind of the norm. Back in the day, there was a thing called EC2 Classic, which is fortunately going away, and it's been replaced by the normal paradigm of VPCs and security groups. And what security groups look like are essentially a firewall. If you think about it in terms of your home router, your Wi-Fi router at home, where you can poke specific holes in to let whatever traffic in or out you want, your DNS traffic, your NTP traffic, your web traffic, maybe you've got a camera. If you have got a camera, I want to talk to you later, because I want you to make sure you get a password in that sucker. But that's just like a firewall. You can choose which IPs, which CIDRs you let in, and moreover, what you let out, because not all EC2 traffic needs to allow ingress traffic. If you've got applications that are back-end, they should be in a private subnet, which is non-addressable on the internet, and is obviously not a target that needs, but they may need to get out. Maybe you need to patch them. Maybe you need to do a yum update, or maybe you need to pull down a package. So they do need egress capability. Now, as Adrian mentioned, scaling's a really cool toy inside AWS. You can scale up, absorb loads. You can actually use it for operational things like rolling over armies. As you upgrade your army, you can shoot one, and then you can bring up another one, so you get some really good operational techniques. But that becomes a problem in the firewall world, because firewalls are IP-based. So if you bring up a new EC2 instance with a new public IP or a new private IP, then you've got to reprogram the firewall. So one of the cool things you can do with security groups is you can tell it that it's not an IP it needs to think about, it's actually another security group. So in that way, and in this case what we've got here is an application security group, and that's got a rule that says I'm going to allow any traffic in from my web server, and I'm going to let any traffic out. And then the web server is basically saying, I'm going to allow anything in port 80. It's a web front end. It just allows anything kind of HTTP traffic. So using security groups is really important. The next thing we want to do is visualize that traffic. Now, if you're familiar with things like NetFlow, which is basically a 5-tuple, the 5-tuple describes your IP connection, your source IP, your dest IP, your source port, your dest port, and then the protocol, be it UDP, TCP, ICMP, what have you. You want to have visibility. And if you think about flow logs as being your visibility into what's crossing the VPC boundary, because that's really what's pertinent to your application. And you can view it at the entire VPC level, or you can look at it at the EIP or the instance level to see what traffic's coming in. And then the last thing is NACLs. Now, network ACLs work, if you're familiar, like router ACLs. They're completely stateless. They simply block whatever they're told to block and allow whatever they're told to allow. Don't get that wrong. Now, the difference between the ACLs and the security groups is this. Security groups have a default deny rule, so you explicitly have to poke holes out or in. NACLs are default deny. So anything in there is going to be denied by that very last rule. So typically what you'll see is that there's a rule just above it that's going to let everything in, right? So that's just something to be aware. So if you want to explicitly go and block stuff, then you put an additional rules in here above that rule 100. Okay, why is that important? Right, so talked about gaming. As an industry, gaming's really, really tough. And there's some really interesting reasons around that. First of all, there's their ecosystem. Their ecosystem's actually quite complex. because they've got a number of different applications and services that are very dissimilar. You know, you've got the web portals where you go and create your characters and you sign in and you buy your merchandise and what have you. Then they've got the actual game servers, and these are big, beefy servers where it's real-time processing and you've got multiple players, maybe even get multiple games on a single server, and they're doing a whole different thing. Then you've got matching servers that are playing join the dots between the servers and who's coming on and matching up who's ready to play. And then relay servers, which are things like chat and peer-to-peer connections. The thing that makes this really hard is that these games are super, super latency sensitive. If you've got a web request going out there, do you really care if CNN.com resolves in 3 milliseconds? Do you really care if it resolves, frankly? But anyway, but I mean, a few milliseconds here or there doesn't really matter. If you're just about to frag someone and your gun freezes, you're into the new game. So I mean, it's really important, especially these competition games with the professional guys where every millisecond counts. So that's really, really important. They also are kind of load sensitive as well. So there's a number of reasons that these, and we'll talk about in a minute, that they're different from other things. Now, the web portals, this is the usual suspect. You're probably bored of this slide by now, but it is really important to see that if you've got a web portal, you're in really great shape. You've pretty much got access to all the AWS services that are going to help you protect yourself from DDoS. But the rest of the services tend to be UDP based. That means they can be spoofed. That means our favorite Mirai or NTP Reflection Attack or DNS Reflection Attack is very effective against this kind of service. Latency, as I mentioned, is a big problem. So you can't put multiple layers of routers and firewalls and IPSs and WAF because it just ruins the experience. And you can't scale a game very effectively. These multiplayer games are typically hosted on a single point. You can't be sharding your servers because then you're going to get a different gaming experience and you're going to have to copy all that real-time data. So typically they're very statically associated with a particular server. However, there are things you can do. If you've been following along with DDoS and AWS, you maybe recognize these things. These are the best practices that we've been talking about. These are things that you can do in AWS to secure your application. And Jeff and I authored a white paper. It's available on the internal website in the AWS security white papers. You can download it, full of best practices, really handy. It doesn't work so well for gaming servers. So if you've got UDP workloads, and it's not just the gaming servers, it can be voice over IP, it could be video. There's a number of different applications that have these kind of problems. But there are things we can do. Reduce the blast radius. We'll talk about that in a minute. This is my favorite one. DDoSers have been doing this for years. They play whack-a-mole. They move things around. They change the IP addresses so you can't find them. With AWS, you can change the game on them. I'll talk about that too. The first thing, reduce my blast radius. If you put all your eggs in one basket, it's a bad situation. It's an old proverb, but it's very, very true. If you've got your FTP server and your mail server and your voice application and your API gateway all in the same server, if any one of those services gets attacked, it affects every other one. So we don't do that. Shard your services. Service segmentation, and this works well for gaming. You can reduce the amount of effect. Gamers are a funny lot. They kind of move on. They're not actually too bothered. If a game blows up, they just jump on the next one. If you can reduce that blast radius so it's a game that's being affected, you've got 200 other games that are quite happy. And you can do this for other applications as well. Restrict access. If you know who your clients are, you can set your security groups so that they're the only people that can connect. These big multiplayer games know exactly who's connecting. They know the source IP of every single player because that's what the matching server does. There's many applications out there that have similar characteristics. Maybe it's a peering application with a sister company. You know the IP range that it has, so you can take advantage of that. On host, you can do on-host filtering. IP tables, net filters is great. You can do all kinds of stuff. We use it in AWS a lot. You can do rate-based limiting. You can drop stuff. You can fragment. You can pick up a lot of garbage in there that makes it really, really easy to drop bad traffic. You can move the target. One of the problems with on-prem is if you're really lucky, you've got a B-level address. That's a /8 for the new folks. You may have a C or a handful of Cs /16s. The problem is they're contiguous. The DDoS guys are not stupid. They know that if you've got 10.1.120, you've probably got 10.1.121. So they can basically do a host scan across your IP space, learn it, and use that to your advantage. AWS has lots of IPs. And I mean a lot. Not as much as we'll have when we get IPv6 everywhere, but we have a lot of IP space. That means you can get lots of different IP addresses. Not only that, the IP addresses that you get in AWS are non-contiguous. So the DDoSers can't assume that your IP space is contiguous and just hop from one to the next. So if you get an attack, you can simply pick up that EIP, move it off into a safe zone, and get yourself a new one. The good thing about this is also you don't have to get rid of that instance. You can do forensics on it. You can look at it. You can use it like a honeypot to figure out what those attacks are doing. So, Jeff talked about some of the attributes, some of the services. Adrian told you how it works in practice. I'd now like to invite up the founder of TeamSpeak to speak to you and tell you how this works in practice. I like big hand for David. Thank you.
Hi, so I'm the founder of typefrag.com, and we provide TeamSpeak hosting. So how many people here are familiar with TeamSpeak? Have used it before? Great. Okay, so when TeamSpeak goes down, do not blame us, blame the DDoS attackers, because that's the cause of almost 99% of downtime on TeamSpeak. So TeamSpeak, for those who aren't familiar, is a client-server-based voice communication program. It's very popular amongst online gamers, and those gamers, in order to gain an advantage in the games, will sometimes launch DDoS attacks. So if you're playing a competitive game and you're playing with your team, you know the opposing team is using voice communication, and you want to knock out their comms. It's a common military strategy, right? You launch a DDoS attack against that server. So this is something that's cost us a lot of time over the years. I've a lot of sleepless nights trying to defend against DDoS attacks. And one of the things I learned is that there's really no silver bullet for DDoS attacks. So originally, we used to co-locate our network on various providers, Equinix, Internap, these sorts of companies. And the common DDoS defense tactic was to over-provision our network edge. So if you can imagine, at the network edge, we have multiple 40 gigabit connections. Then down to our switches, we have 10 gigabit connections. Then down to our individual machines, it's 1 gigabit connections. So when DDoS attacks started to get up past 40 gigabytes, we needed to block 75% of the traffic at the network edge in order not to congest the cross connects, and then block an additional 90% traffic at the cross connect, or rather at the access layer, in order not to overwhelm the individual system. So this worked for about 3 years, but eventually those attacks got so large that it became cost prohibitive to continue to block at the network edge. So we did a couple things when moving to AWS. First, leveraging AWS's global infrastructure is extremely important. Once you move to AWS, you're going to get the built-in protection that Jeff's team provides, and that blocks about 90% of service-impacting DDoS attacks. But from there, you can do a couple of other things. First, you can minimize the attack surface. So using NACLs and security groups, limiting the amount of ports that can be attacked is very helpful. And then reducing the blast radius, and this one is not as obvious. So when you minimize the attack surface, that's kind of the same as in a network, in your traditional network environment, right? You're applying NACLs at a port basis, so that's pretty common. But reducing the blast radius, that's something that's kind of unique to AWS. And we'll discuss that in a bit here. And then fourth, which is really cool, is to be able to automatically mitigate those attacks. And we'll get to number 5 too, which is analyze and learn, which is a really, really important one. So one of the prerequisites for minimizing the attack surface is using one network access control list per VPC subnet. So in AWS, normally you have one NACL that can be applied to multiple subnets, and then you can obviously launch multiple instances into the subnets. So this is kind of an uncommon setup. You want to actually use one NACL per VPC, one instance per VPC, and that allows you to control these on a per instance basis. So as Andrew alluded to, you can dynamically whitelist and blacklist users, and you're going to want to be able to do that on a per instance basis. So that's an important building block in our setup on AWS. Another important thing from this slide is the use of elastic IP addresses. So these can be changed on the fly, which is extremely important when mitigating the attacks. We'll get to that soon. So here's a quick snapshot of our NACLs. Here we reduced the attack surface from what was normally 65,000 plus ports down to about 100. You might notice also, if you look really closely, the ephemeral port range for the instance, that opens up a few other thousand ports. You can actually limit that as well if you adjust it on your instance and adjust it in the NACLs. And then here on the right, you'll see that we are using an elastic IP address. The elastic IP address NATs to the internal IP address. And if you remove that elastic IP address, you can still route and connect via the private IP in the subnet, which is really cool. Or if you swap it out, you can stop the attack right in its tracks. And we're going to demonstrate that later. So this is the one that was not as evident moving from a co-located environment onto the cloud. So when we first moved to AWS, we looked at our instances and we saw that they had dual Xeon, 32 gigabyte RAM. So we looked at an instance class at AWS that was comparable. And we quickly learned that that's not exactly the best strategy. If you can use smaller instances, use more of them, spread your customers across them, you'll actually reduce the blast radius, so any individual attack will affect less users. Like that. So attack mitigation. This is pretty simple. You can get pretty complex with it depending on the type of monitoring you set up and how you actually mitigate the attack. But in this example, we're just using CloudWatch alarms that trigger Lambda functions. Lambda is a serverless compute platform offered by AWS. And that Lambda function will actually switch over the IP address on the instance. Another important component is Route 53. You could use your own DNS. I would not suggest doing that. Route 53 is great, costs very little, and is programmatically accessible. But of course, you could use your own DNS infrastructure if it was programmatically accessible to change the record for that DNS. So first thing, you want to detect the attack as soon as possible. The faster you detect it, the sooner you can mitigate it. With CloudWatch, you can do that usually in about 60 to 90 seconds. If you roll your own monitoring, you can get that down below 10 seconds. Once the attack is detected, you're going to want to trigger the Lambda function to change the IP addresses on the instance. And also update Route 53. Once you do that, you're effectively mitigating the attack. The elastic IP continues to get hit. As Andrew suggested, you could play cat and mouse. You could put it on another instance and start collecting data about the attackers. Or you can just throw it away and use the new IP. Once that's done, the attack is mitigated. So I put together a short demonstration. Unlike BNY Mellon, we're not a systemically important institution. So I did record a demo of me attacking one of our test instances. Probably not the wisest thing to do, but I'm going to share that with you right now.
Connected.
Hey, Nathan. Thanks for joining me on TeamSpeak.
Not a problem.
So I need to trigger an elastic IP address change by simulating a denial of service attack.
Okay.
So I want to show what it looks like from the user's perspective. So if you could talk while I run the simulation, it'd be very helpful.
Sure. What do you want me to talk about?
I guess you could tell me a story about your adventures in the new Battlefield game.
Okay.
All right, so I'm going to go ahead and start the sim now.
All right, well, I'm definitely enjoying the game. They've got this new campaign mode that's a lot of fun. The other day I deployed down a medic with the rest of my squad and we were attacking the trenches. We managed to get all the way up to the trench and I jumped in it after pretty much the rest of the squad got killed. And I'm running down the trench and this guy pops up in front of me.
Hey, Nathan, are you there? It cut out. So that's the attack, obviously disrupting the voice comm. All right, looks like the elastic IP address change was triggered. Any second now, it should be reconnected.
Connection lost.
That was
Connected.
just as I got revived. I swear I was about 20 kills at that point.
So you got cut out there for a good 20 seconds.
Oh, okay.
Not too bad, though. I think it took maybe just about a minute.
Not bad. What did you think of the 20 kills, though?
So following these three simple strategies, we were able to reduce the impact of attacks on our network by 99.9%. And so first, having moved to AWS, we saw the number of service impacting attacks go down from roughly just over 50 to below 5 each month, which was a significant drop for us. And that's service impacting attacks. So if we get hit probably 100 plus times a month, and seeing only 5 of those actually come through and hit our instances was a huge improvement. And after making that move, I finally got some sleep with this problem. But second, reducing the surface area and spreading out the number of instances to reduce the blast radius, we were further able to reduce the impact of any single attack from roughly 2,000 concurrent users connected down to below 200. So that was another order of magnitude improvement. And then when you add in the automatic DDoS mitigation, you're going from usually a 15-minute response time and a bunch of pagers blowing up down to 90 seconds. So taking that all together, we measure our impact in terms of user minutes per month. We went from about 1.5 million user minutes per month, and that was out of about 5 billion user minutes from our users down to below 1,500, which was a great improvement. So the last thing I wanted to talk about was attack analysis. And this is a really, really important piece of DDoS mitigation strategy, and it's not talked about enough. But that's identifying the attackers and then holding them accountable. And that could be just submitting abuse reports to the offending networks, or it could actually be tracking down the attackers. And we've had some success actually doing that and prosecuting attackers against our network, believe it or not. And so we built this cool little app. It's a single-page app. If you're not familiar, that's essentially you have static content that you can host on CloudFront and S3, and that serves up the primary user interface for your application. And in the back end, using Lambda and API gateway, we built a RESTful API that actually analyzes the VPC flows. Now, we could have done this with Kinesis and Redshift and these other Amazon services so that we would have historical data, but we wanted to do this on demand. And so we didn't want to spend thousands of dollars keeping these VPC flow logs and running the queries against them continuously. We just wanted to look at a single attack after it happened, identify the targets, and then prosecute. So we built this really cool tool, and it cost us about $5 a month to run, and it gives us reports like this. In this particular case, it was a non-service impacting attack that targeted port 80, one of the ones that we block. But running the analysis in Lambda, we were able to identify over 1,000 source IP addresses that contributed to this attack. And so we tracked them down, submitted abuse reports. And this, again, this is really important, particularly as IoT and these other things come online, is knowing who the attackers are. If you fight the good fight, then you can reduce the number of bots in the botnet, which helps reduce the impact of DDoSes for everybody. So that's all. I'm going to hand it off to Jeff here. I don't think we're doing any questions, but he's going to show how to submit support. Thanks.
All right, thank you. We've learned about how you mitigate or how we mitigate DDoS attacks in the cloud and how you can use our services to take advantage of those mitigations so that when we work together, you can benefit from the scale and resiliency of AWS to optimize for both performance and availability of your application in the face of DDoS attacks. But what happens when the automated systems don't work as intended, or the architecture that you've built doesn't do quite what you thought it was going to do, and that attacker was able to find a way around and impact the availability of your application? What's next? And so on my team, on the DDoS response team, we spend a lot of time thinking about how can we make life better for AWS customers? In that very small percentage of cases where things just don't go as planned, what can we do for you to help you out? And so we thought about this, and the feedback we were getting from a lot of customers was, these systems work great normally, but what happens when they don't? Like, I don't really know what my next step is. Like, what is my recourse? And so we partnered up with AWS Support, and we built a new capability into the AWS Support Center. And it's really quite simple. You just go to the AWS Support Center, assuming that you're subscribed to at least business or enterprise support. You click Create a Case. And then you have a new service type. And the new service type is just this generic description of distributed denial of service. Behind the scenes, that's causing your case to not be routed to a specific service representative, but rather to be routed to somebody in AWS support who specializes in security issues like DDoS attacks. And then you just provide a brief description of what's going on. What do you know about the attack? What impact are you seeing? And then you just click to chat or click to talk to us on the phone. And depending on the level of support that you've purchased, you can get in touch with us pretty quickly. So that's it in a nutshell. To learn more about the different techniques that you can use to architect your applications and some of the things that we discussed in terms of the mitigations that we provide, if you go to aws.amazon.com/security, you can download the AWS Best Practices for DDoS Resiliency. And you may be familiar with this white paper from years prior. This is actually a new version that's only a few months old. So it has a lot of new tips and tricks and a lot of new information that you can use. I want to thank everyone for coming out. And I want to place a lot of emphasis on this slide, because this is actually really important to us. It's not just fun data. It's not just nice to have data. Every year, we take a deep look at this data, and it helps us decide, are we going to come back next year and give you more information about DDoS attacks, or how are we going to create the security track? So your feedback on this evaluation is really important to us. Thank you for coming.